Good stuff. So that's all running smoothly, it looks like. We can go ahead and get started. Thanks everyone for joining us this morning for this webinar. As mentioned, my name is James and I'll be hosting the webinar from EDINA as part of the University of Edinburgh. I'm going to hand over just now at the start to Stephen Thompson from the Data Lab, who's going to share a couple of slides about the Geospatial Fringe and the Data Lab. So over to you, Stephen.
Cool, thank you, James. I'll just get my slides up. If you could let me know if you can see that, because I can't see Teams anymore. If that's coming through for you. Okay, cool. Yeah, so thank you and good morning to everybody. Like James said, my name is Stephen Thompson and I'm the Events and Community Manager at the Data Lab. I'll try not to take up too much of your time this morning, but I just wanted to kind of come on to say hello. And for those of you who aren't already aware, give you a little bit of information about the Data Lab community and also the Geospatial Fringe, which we've got running throughout August. And apologies if you hear my dog who's just woken up and started to whine next to me. So the Data Lab community is an online community platform that we established a couple of years ago, and it was set up as a place for anybody who's interested in data and AI to come together. Whether you're a data or AI professional, whether you're a student or an academic, or even if you've just got an interest in data and AI and you want to learn a little bit more about it, the community was set up as a place for people to come together, connect with each other, kind of grow their networks, learn and kind of share resources with each other. We launched it in September 2021, and since then we've grown to over 5,000 members from over 80 countries around the world. So if you are looking to grow your network and kind of be involved in the data and AI community, then it's definitely a great place to be. In the community, we've got an events program. We run regular meetups and webinars. We kind of like this month, we've organized the Geospatial Fringe. We also have an events board where you can find out information about all of our upcoming events, as well as any events that any of our members are organizing. Anybody can add an event there, whether you're organizing it or you think it would be of interest to anybody else in the community. And we've got a mentorship scheme, and we're always looking for mentors. So if you're looking to become a mentor, please get in touch. And we've also got a jobs board and a space for courses and resources. So the Geospatial Fringe, I guess the reason we decided to organize this was that we saw there was quite a considerable interest for geospatial data within our community and within the wider data and AI ecosystem. And we thought it'd be great to bring together all of the different organizations and networks who were involved in geospatial data to try and celebrate this and discuss all things geospatial. We wanted to get as many organizations who are involved in this together to build a program of events that could really showcase geospatial data and everything that it has to offer. And we want to try and help raise awareness and understanding of geospatial data and shine a light on some of the organizations that are working in the space. So today's event is the third event in the program, and we've still got another event, another 5 events to look forward to. So this is some of the events that are coming up on the screen at the moment. Events are taking place online and in person in Edinburgh and in Dundee. So if you are interested, please check them out and sign up for any of the events that you're interested. All of the events are free to attend. So yeah, have a look, check them out and sign up for anything you're interested in. You can find out all the information about all of these events on the Data Lab community. And I've got a slide in a second that'll lead you there if you're not already a member. So just a quick mention of some of the organizations that are involved in the Fringe. We're really proud to have quite a lot of the kind of big players in Scottish geospatial data involved. For example, Nature Scot, EDINA, AGI, Geovation Scotland. We've got the Dundee Data Meetup, TechScaler, Abertay Cyber Quarter, Scottish Government and Location Data Scotland have all got events, and Teradata, sorry, have all got events still to come. So yeah, definitely check them out. And as I said, if you want to check out the events, you can do so by scanning this QR code. It'll take you to the Data Lab community. If you're not already a member, you can sign up and create an account for free. And if you are, then you probably already know this, but along the top of the events board is where you'll find all the information about the upcoming events. And finally, just a shameless plug from me that if you are attending any of the events and you're finding them valuable and you'd like to post about them on LinkedIn, please do tag the Data Lab community. Anything that helps us to kind of spread the word and make sure people know what we're up to. And that's everything from me. So I will pass you back over to James.
Thank you very much,
Again.
Stephen. You
There we
can
go.
now hear me okay, hopefully. Thanks, Stephen. Really great introduction there. Nothing shameless about plugging some cool stuff. So everyone, please do go have a look at the Data Lab community. Sign up if you haven't. There's some cool stuff happening in the Geospatial Fringe. And lots of stuff coming up as well. So thanks very much for that, Stephen. I'm just sharing my screen now. Hopefully you can all see that. If other people join the lobby, Stephen, I might ask them. I know you have to jump off in a little bit. If you could let people in, if that's okay. But again, thanks everyone for joining this morning. Good morning, everyone. My name is James, and I'm the Notable Service Manager here at EDINA within the University of Edinburgh. At EDINA, we develop services and solutions that help people learn about, visualize, and work with code in the services that I manage specifically, but also largely with maps, which is an area of expertise at EDINA. So it's my pleasure to welcome you to this morning's webinar titled The Code to Mapping New Horizons. We'll be looking at ridge maps and orbital solutions in Noteable, which is the service I'm in charge of. And this is part of the Geospatial Fringe that Stephen already introduced. So I won't go into much more detail on that. What we'll be doing today is we'll explore the dynamic intersection of geospatial data analysis, satellite technology, and also solutions and tools that make it possible for these things to come together. We'll be discussing how we can leverage specific tools like Jupyter Notebooks, which are one of the main tools provided in Noteable, and how these can help evolve and revolutionize our approach to handling and interpreting complex geospatial data. The presentation today will cover a number of topics, technologies and applications of them. We'll start first with an overview of Jupyter Notebooks and how these work. I'll touch a little bit on Noteable, the service I work on, and how these applications and tools can be used in geospatial analysis. From this introduction, we'll go into a bit of a deeper dive into how code and geospatial look and work together, focusing on ridge maps with a case study from the Lake District. And then we'll do an exploration of satellite congestion in low Earth orbit, and the implications and geospatial challenges of this, before we wrap up with a discussion on the future directions and takeaways from our findings, with some space at the end for Q&A, hopefully. I hope this session inspires new ideas and collaborations in the geospatial data analysis community. So without further ado, let's dive into the first topic. We're going to look at the power and versatility of Jupyter Notebooks in geospatial analysis and see how this powerful tool can be used in this area. So once again, just to mention, this event is brought as part of the Geospatial Fringe. To kick things off, let's have a look at the themes and the connections of what we'll be covering today. We're about to really start exploring some of the exciting intersections, or I think so at least, of code and geosciences, which are two fields that connect in some unique ways. They create varied opportunities and some very cool insights and advancements that we've seen. So the primary tool for this journey is Jupyter Notebooks. And when I refer to Jupyter Notebooks, these are a super versatile file format and wider tool and platform, which is essentially perfect for data manipulation and visualization. It's really become a fantastic asset for geospatial analysis, as it provides a web-based interactive computing environment, ideal for the field and widely used across industry. The dynamic design of Jupyter Notebooks, which we'll have a look at in the following slides, allows for exploring data on the fly, as well as collaborating seamlessly with others. So moving forward in the presentation, we're going to look into exactly how Jupyter can boost geospatial analysis capabilities and showcase its power and flexibility through some actual examples and applications. That means that every time I'm saying Jupyter, I'm referring to the Jupyter ecosystem and the Jupyter platform, but also specifically to something called Jupyter Lab I'll be talking about, and that's the latest interactive development environment for notebooks, for code inside of notebooks, and for data management inside of notebooks. So when I say notebooks, I'm also referring to computational notebooks, which are a wider term for tools like Jupyter. Jupyter's flexible interface supports customized workflows in data science, scientific computing, computational journalism, and machine learning. So its uses span far and wide in geosciences and beyond. And its modular design lets you add extensions that can enhance and enrich its functionalities. So next, let's jump in and see how these tools can revolutionize the way we actually approach geospatial data. So here's just a couple of things that are important to highlight in asking where's the space for code
in geospatial and where does it fit in. I've just summarized a few of the areas where coding proves beneficial in this space, starting with automation, which really means when coding enables automation, it means we're automating repetitive tasks like data collection, cleaning, and transformation of data. So for instance, instead of manually entering data from multiple sources into a script that you're writing, we can write a script that gathers the information automatically on a scheduled basis. This can help save a tremendous amount of time and minimizes human error, which leads to more reliable data sets and analysis of those data sets. We can also automate the organization, actions, and structure of objects, such as, for example, satellites, which we'll look at later in the presentation, and that allows us to track real-life objects. And we can then find trends, risks involved, and this impacts larger business ventures like investments. Accuracy is also a part of code in geospatial. Algorithms or recipes written with code can help us process large data sets consistently and systematically. And that ensures that there are no discrepancies due to human oversight, a typo, anything that can happen. So for example, we can apply the same data cleaning process via a script, which helps also ensure that each data set is handled uniformly and helps improve the overall quality and accuracy of the data that we're using. And this helps minimize complexity, as well as giving us some more options to work with complexity. Coding allows for the creation of advanced models and simulations that would be impractical or impossible to perform or design manually. So for instance, a model that can predict urban growth over the next given decade based on various input parameters like population, economic indicators, available land, etc. These can be developed and run using Python in a Jupyter notebook, and we'll have a look at what that looks like in a visual way in the next few slides. Such computational tasks are usually far beyond a single human's hands capabilities without the aid of programming. So another important area for these tools is reproducibility, which I'll mention later on. So this links to geospatial and how code works in geospatial and platforms like Noteable, as they include libraries and tools, and Jupyter Notebooks, for example, supports a variety of Python libraries specific to that programming language Python, such as pandas, GeoPandas, which you can see here on the bottom right-hand side, their logos, and NumPy, which are libraries that can be put into Python and are essential now for data manipulation and analysis. Pandas, for example, is used for handling tabular data structures. GeoPandas is an extended version of Pandas, and it's designed to work with geospatial data. So now that we can see some of the uses for code in geospatial and this area, let's have a look at some of the actual concepts and applications in the next slide. So moving on here, it's a key area where we can understand the tools and techniques when you apply geospatial data and code. So you can see where these concepts, ideas, and where code can really shine. I think starting off on this slide first, it's important to understand at a high level some of the different types of geospatial data that we work with. Geospatial data is generally categorized into three main types, shown here on the slide: raster, vector, and satellite data. Raster data consists of pixelated data like aerial photos and satellite imagery. Vector data represents features like points, lines, and polygons, different shapes, which is typical for different types of maps and geographical information systems, so GIS data. While satellite data, on the other hand, offers a bird's eye view of the Earth. So similar concepts and ideas, but they can provide very different uses and value in different spaces. So when these come together, some interesting stuff can happen. The different types of geospatial data are powerful tools in themselves. Their applications span many real-world scenarios. So as an example, in urban planning, vector data can help city planners design infrastructure and optimize land use. Satellite data, on the other hand, can provide up-to-date imagery for monitoring things like urban expansion. For environmental monitoring, and say, for example, understanding the ESG impact of a business or of an institution, raster data can help create continuous surface maps, can help track vegetation indices, and then that can also be supplemented by other types of data like satellite data, which can help track ecosystem changes, deforestation, climate change effects. Another example is an emergency response. Raster data can help predict risk areas using flood maps, while vector data can map critical infrastructure and evacuation routes. And then satellite data can be added to the equation to offer real-time imagery for damage assessment and then the disaster recovery efforts. So hopefully this helps illuminate how geospatial data is used by a diverse group of authors and audiences, and how it takes form in different ways as well. Honing in a bit more on the data science applications of it, it can help develop new analytical methods and models, and researchers leverage geospatial data to generate new insights and publish their findings. So professionals in various fields as well can span urban planning, environmental science, public health, and they're all using geospatial data in similar and also different ways to inform decisions and improve outcomes. So if we understand these applications and the types of data involved a little bit better, it can help us appreciate the importance of the effective tools that we can have a look at in more detail for geospatial analysis. And in the next slides, we're going to go a bit more deeply into specific examples, and we'll see how tools like Jupyter Notebooks and Noteable can enhance our work with geospatial data. Cool, so this is quite a crowded slide. I'm not going to go through all of it, but it helps give you an idea of the extent of Jupyter Notebooks. It's really a project, an open source project that spans thousands of authors in some capacity. So just like the Planet Jupyter, it's a big ecosystem. It's essentially a nonprofit initiative that provides free, powerful tools for interactive computing and data analysis. It's very versatile. It's modular. It can be used in a plug and play way with lots of extensions. And again, it's an 100% open source ecosystem. So not only is it free to use, but making these tools accessible for developers, for everyone to work with, can really help expand the technology and span wide with who can contribute to the technology. And this brings particular uses to students and teachers, which is the audience that we're mostly involved with here at the university. But it's also used more widely with researchers and professionals. The project itself consists of this rich ecosystem that you can see listed here. It's full of different software applications and standards, and each one of them serves a unique purpose. So I'll go through a couple of the key components. IPython is really a legacy term. It's the foundation for that interactive computing that takes place in a notebook. So sometimes you'll see reference to it, but it was what essentially Jupyter and .ipynb, which is the file format for IPython notebooks. That's where that comes from. There are a couple of other tools that make Jupyter very powerful. So Jupyter Server helps you support Jupyter notebooks in a more distributed way. It helps create server extensions. It helps create projects, and it's a way to also scale use of Jupyter notebooks. So that's proven really helpful for different applications and uses of Jupyter. When we're talking about the notebook itself, and Jupyter widgets fall inside of the Jupyter notebook, it's that interactive environment. If you think of a Word document, but a Word document where you can distinguish where you're writing normal everyday language text and where you're writing code, you start to create this cell-like structure to the document, which is that Jupyter notebook that we're talking about. And then you can go a bit more deeply. If you're working with a console, with a terminal, you can also access that inside of Jupyter notebooks. And then I mentioned earlier at the start, there's the newer version of Jupyter called Jupyter Lab, which is that next generation, all web-based environment. It's really an integrated development environment, an IDE for Jupyter notebooks, code, and data. And it's a more robust and flexible user experience with tons of extensions that you can have a play with. And these span things like packages and libraries and models and frameworks as extensions. It spans new features like assignment management for code is an extension that's available on Jupyter that we make available as an added feature on Noteable. So there's thousands of extensions available, and some of the interesting ones that are coming out recently have to do with AI and integrating different LLMs and different models into the Jupyter Notebook experience. So it's quite a cool, very relevant, very up-to-date interface, which has also quite a long-standing history of development from lots of people, professionals, all the way from people just coding as a hobby. So that's just a glimpse into the extensive capabilities of this Jupyter ecosystem. There are tons more tools and extensions available, and they're continually expanding what you can achieve with Jupyter. What Noteable does, as an example, is it puts together a lot of these technologies and provides dedicated tools for education in a managed way for institutions to access coding environments and scale them up across their institution. So now that we've really set the scene with Jupyter notebooks and geospatial, it's time now in the webinar to see how these tools can be utilized specifically for geospatial data analysis. And we can have a look at some practical examples that demonstrate the flexibility and power of choosing these tools in geospatial. So hopefully you become a bit more familiarized with Jupyter if you weren't already. And it's a good point now to ask, how can we best use this as a tool in the geospatial context? Where's the link here to some actual applications? And to do this, we can first take stock of some of the fundamental principles and the tools that are essential for geospatial analysis itself, and where these mesh with good and effective coding practice. So first and foremost, from the slide at the top, good coding practice is the backbone of any successful project. And there are three pillars that we've chosen here to focus on: efficiency, readability, and reproducibility. Starting with efficiency, efficient code ensures that programs run well, relatively quickly, depending on what you're doing, and don't waste resources. So imagine if you're working with vast data sets from satellite imagery or geospatial records, efficiency can save us valuable time and computational power, which means we have more time to do other things, whether it's free time, and we're also maybe not spending as much money on computational power as we might otherwise be. Readable code is just as important, and that has to do with how others are able to contribute to the code that you're writing, understand the code that you're writing. When we write code that's easy to understand, we're not just doing ourselves a favor, but also helping out anyone else who might read or maintain the code in the future. And of course, lots of us might be coding day to day for individual purposes, but a lot of us, if not most, will be doing it in a way that's in a team setting. So clear naming conventions, thoughtful comments, organized formatting can make a significant difference when you're coding in geospatial and across different industries. And it's like writing a well-structured essay or making a clear map in our case. Clarity is key. So with these two, reproducibility rounds out our trio here. In the scientific community, specifically, results need to be reproducible in order to be trusted, in order to then be applied, especially as this might have knock-on consequences on human lives and the way things are designed and the way policy is made. This means ensuring that when someone else, or even when we ourselves run the same code with the same data, we should be getting the same results. So avoiding hard-coded values and maintaining well-documented workflows significantly aids in achieving this. And this will come clear in the following examples that we'll look at in the webinar, where we've had lots of teams working on lots of different data, and this has come together in a number of research cases. So now let's talk a little bit about the data sources that we have at our disposal. Geospatial analysis relies heavily on diverse and robust data inputs. GIS systems, for example, allow us to manage, analyze, and display geographical data. It helps us do it in a way that's clearer and more functional, and they act as a digital backbone for digital analysis in many ways. Remote sensing data provides a more bird's eye view, quite literally, as it's mostly based off satellite and aerial sensors, which help capture detailed information about the Earth's surface, and this helps us in turn track changes over time and across vast areas. So this data is becoming increasingly valuable and invaluable for everything from environmental monitoring to urban planning. And then there's the GPS technology we're probably all familiar with. And with GPS, we can pinpoint precise locations on the Earth's surface or any object's surface. It's crucial for creating accurate maps and for any field work that requires exact spatial information, such as, for example, when you're tracking orbital congestion or the amount of objects going around the Earth and the challenges that poses. So these data sources, we can hopefully see by now, are incredibly powerful, but their true potential is unlocked when they're used in an interactive environment for analysis. So imagine having the ability to create a flowchart and a diagram that maps out an analytical process, an analysis process, generating detailed plots and helping to reveal patterns in the data, being able to do that on the spot, crafting that code, crafting those maps, and telling a story visually. That interactive capability is exactly what tools like Jupyter Notebooks, what interactive development environments, what Jupyter Lab is able to provide. Essentially, they're not what I'm concluding here is they're not just environments for coding. They are spaces where we can explore, visualize, and share our data in dynamic ways, and this allows for a better exchange of ideas and knowledge between us. So what makes these tools also compelling is the role as a unified platform for analysis. So instead of juggling multiple software applications, you can perform all of the desired computational tasks, data manipulation, whether it's visualization, documentation, that can be done within a single integrated document or a single integrated framework. And such a streamlined approach helps empower geospatial professionals by enhancing the workflow efficiency and promoting seamless collaboration in better ways. So as you can see, making use of these tools, adhering to good coding practice, it significantly elevates geospatial analysis and how it's done. And we can move from raw data to actionable insights, which are supported by robust, interactive, and integrated environments that make it easier for it to be shared across teams, across institutions, and across actors that are using this geospatial data in different ways. So now let's explore some of the principles and tools that come together to transform approaches to geospatial data. In the next slide, we'll have a look at firsthand the power and flexibility of the unified platform that is Jupyter Notebooks and similar platforms. So thanks everyone for tagging along so far. In the first half of the webinar, we've really described a bunch of stuff. So let's dive into looking at some things in a more practical way. So the next topic is Jupyter and Geospace, where we're going to look at how Jupyter Notebooks and Jupyter Lab in particular serve as great tools in various aspects of geospatial work. So starting with data visualization, one of Jupyter's standout features is its ability to create really beautiful, as you'll see in a few slides, and effective visualizations of data. Whether you're creating maps or charts or complex graphs, Jupyter makes it straightforward to transform raw data into meaningful visuals by putting it all in one place. So the ability to see data in visual formats can really help us detect trends and patterns that might otherwise be hidden in raw numbers. And something similar applies to data analysis. Jupyter provides a powerful environment for detailed data analysis, whether we're crunching numbers, doing statistical tests, or integrating various data sets of different provenances. Jupyter Notebooks makes these tasks not only possible, but more efficient and reproducible because of how the file format is laid out and how interactive it is. And also because Jupyter supports multiple programming languages, like the ones included in the name Jupyter, Julia, Python, and R. We can leverage the best tools in these programming languages that are available for any analytical task that we have at hand. And in geoprocessing, that's another critical area where Jupyter shines. Geoprocessing itself involves manipulating and analyzing geospatial data to create new data sets, to extract spatial information, to perform tasks like a spatial join or an overlay, and buffer analyses. And what Jupyter can do is it can integrate geospatial libraries such as GDAL, a translator library for raster and vector geospatial data formats. And it can also integrate to a bunch of others like Fiona and Shapely. And these allow us to automate and streamline these processes. And these capabilities really help with tasks like creating accurate land use maps, analyzing water resources, or modeling environmental change. One of the hot topics also is machine learning, which is a rapidly growing field. Jupyter is at the forefront of this revolution in machine learning and how it's used in geospatial science. It helps to build, train, and deploy machine learning models, which can be done directly within notebooks. And that's helpful for predictive modeling and pattern recognition in geospatial data in particular. So, for example, we could use machine learning to predict areas at high risk of flooding, and we could do that based on historical data or classify land cover types from satellite imagery, for example. Next is documenting and reporting, which is crucial in geospatial as well as anywhere else you're working with data, essentially. And new Jupyter Notebooks are quite exceptional here because they help us combine code. We can put results, visualizations, and narrative text in one place. So that means that anyone reading notebooks could follow through a thought process step by step from the raw data to the final insight. So it helps create what we call a computational narrative. And that's a powerful way to ensure there's transparency in how data is being cleaned, used, analyzed, and made more reproducible. And additionally, Jupyter Notebooks can be easily shared and published themselves. So that makes it more simple to collaborate with colleagues and present findings to stakeholders, whether that's an educational institution or a business transaction. So to wrap up this slide of how Jupyter is used in geospace, it offers a comprehensive platform for data visualization, geoprocessing, ML. It empowers us to handle complex geospatial tasks more efficiently and effectively. And a key benefit here is that it's all within a single integrated environment. So by leveraging the full capabilities that we have here, we can really transform how we approach geospatial data and make workflows more streamlined, analyses more robust, and findings more easily communicated. So should hopefully become more apparent in the next few slides. So in this screenshot on this slide, we go into the heart of the workflow that we've been talking about, and that's the interface of a Jupyter notebook. So on the screen, you can see a screenshot of the Jupyter interface, which showcases lots of integral components that make this tool powerful and user-friendly. I'll go through a couple, and then we'll go over the next slides, which have a few other visuals. So first off, at the very top, we have the header highlighted. That typically includes the name of your notebook, and it gives you a quick reference to what document you're working on, because you'll have a directory which will list all of the different documents you're working on as part of your workflow. And it's a simple and effective way to keep track of your projects and data sets. Below that header is the menu bar, where you have a set of options for file operations mostly. You can edit, view adjustments, and more. It's kind of like a Word documents file, but it has a few more relevant things for coding. And it consolidates kind of the number of controls that you have in an accessible format. Moving down, we have the toolbar, which gives you quick access to lots of common tasks you'll be using in a notebook, saving your notebook, adding cells in a notebook, so you can see the cell where it says this is a markdown cell. That's a cell where you're going to be putting in markdown language. The one above it, where you print hello world, that's a code cell where you can run using your keyboard or using that play button in the toolbar that lets you run your code. So we can highlight the code cell again, where you write and execute the code. In the screenshot, you can see an example of it where the code is running and Jupyter is processing that code and displaying the output directly below the cell. So that's a really fantastic interactive environment, because you can immediately see the output when you're experimenting with code, say you're quite new to coding, and also when you're running an analysis and tweaking your approach on the fly. Next up, we have markdown cells, which I briefly mentioned. They're equally important, though, because they help you write rich text, explanatory text. You can write headings, bullet points. You can make the text more semantic, and you can change the formatting of it. This can be in a raw markdown cell where we can see unformatted text with markdown syntax. But once the cell is executed, so on the bottom where you see the rendered markdown cell after pressing Shift and Enter, there you're going to be able to see the rendered displaying formatted content. So that's really helpful for writing explanations and notes, and you can start to see how you would be formatting a document like you would on Word, with a table of contents, with your headers and titles, with your figures. You can do that while you're meshing in code as well in a Jupyter notebook. And it's that synergy, that meshing in of these elements, that facilitates a really seamless blend of coding and documentation, where you can execute code, immediately see the results, and then document your thought process or findings all in one place. So it's a really simple example here on the slide, but in more complex cases, it really helps save a lot of possible time or headache when you're analyzing bunches of data as you do nowadays in industry and in education. So this integration is really helpful in teaching and creating tutorials and reporting results, but also really any scenario where clear communication involving code in your work is essential. So to sum up, the Jupyter interface here is really intuitively designed to enhance productivity and collaboration. The header keeps you oriented, the menu and toolbar give you quick access to the essential functions that you need. And the combination of code and markdown cells that I've mentioned really is what allows for that dynamic and interactive workflow. So utilizing this, geospatial professionals are performing sophisticated analyses, and it helps them create well-documented reports with ease. So now's probably a good point on this slide to talk about how you can start using Jupyter Notebooks if you're not already, and start exploring them if you would like. There's a couple of different places and flavors you can get. So whether you're trying it out without installing or you're setting it up on your machine, there's a couple of ways listed here. I won't go into huge detail on them, but just to run through a couple of them. Try Jupyter on the top left is a really great way to get your feet wet with Jupyter, because you can just visit the Try Jupyter website, and it's a free online service that helps you get started with experimenting with Jupyter notebooks. You don't need to install anything. Similar with Jupyter Lite. And then you have a couple of more proprietary versions of Jupyter, like Google Colab, Azure Machine Learning Workspace, Amazon SageMaker, and the Planetary Computer, which is helpful for large-scale environmental and planetary data analysis. And there's a couple of ways you can also install Jupyter on your local machine. You can use Conda, which is one of the most straightforward ways to install Jupyter, short for Anaconda. It's a package manager from the distribution platform Anaconda, and it also helps package installations run smoothly and ensures that all of the dependencies, all of the key connection bits that are happening between the libraries that you're installing on Python and in a Jupyter notebook, that those are all working correctly and as expected. And you can do similar things with Mamba and with pip. Pip is for those who prefer Python's own package installer, and then Jupyter can also be installed using this tool. So if you run something like a command pip install Jupyter in your command line, it'll install Jupyter. So you could do that on your device just now, and then you would get Jupyter added into your local machine. And then there's a couple of more involved, interesting ways you can also build installations of Jupyter. Like with Docker, you can create a containerized way to run Jupyter. So if you're using Docker, you can download and run a Jupyter Notebook container, and that can already contain all of the necessary dependencies. And that's in a way what we do with Noteable. And it's a method that particularly is helpful for creating reproducible environments and is ideal for larger collaborative projects and spaces where consistent setup across different machines and different users is crucial. So just to summarize this slide, whether you prefer to try Jupyter Notebooks online without any setup or take the step to install it, there are plenty of options to get you started. And Noteable itself is one of the options that integrates a number of technologies to make notebooks available from a virtual course webpage specifically. So now here's a closer look at the Jupyter Lab interface, which is that newest flavor of Jupyter. It's a highly intuitive, and it's been designed to boost productivity and enhance the Jupyter experience. I'll walk through a couple of the main components. So the main menu provides access to those ranges of options like file operations, editing, running code cells, and more. Very similar to the menu bar in the previous Jupyter version and other applications. What has changed, moving over to number 2, the right sidebar, that's where you find essential tools and navigational aids with your file browser. From there, you can also find your launcher, which is the starting point for creating new notebooks, as well as terminal console sessions and other activities and extensions. You have the right hand sidebar, number 5, which is the panel that hosts a range of tools and gives you some extra information. So here you can find variable inspectors or other extensions that you may be using while you're analyzing your code. Right in the center, you have the notebook, the center of the interface, where you're writing and executing code. That's where you're going to write markdown cells. You're going to visualize your results. And then you also have access with 7, the code console, with 8, the code console. That's usually located alongside the code console and displays some logging information. That's very helpful for debugging, and Jupyter Lab has had some updates to its debugger and tracks the execution of code to make sure you're keeping an eye on any issues that might come up. So this interface is a newer version of Jupyter. It's designed to be a bit more functional and user-friendly. It has that main menu for a centralized hub. You can move windows around in a more interactive way, so it's a bit more personalized as well. So using this, you can take more advantage of Jupyter's powerful capabilities and be working with the latest version. And here's a slide to kind of sum up the Jupyter Lab interface. At the heart of the notebook is that place where you're writing your code, where you're writing your markdown data, where you're analyzing your code. So here we can see on this slide, we have some data, and we have opened a CSV file using Pandas, that library that was mentioned earlier, and we can see the output of that as a table in Jupyter Lab. So now we've seen Jupyter Lab, we can go into an example of how Jupyter is used to build rich maps. Let's start off by asking, what are ridge maps? They're a compelling visualization technique for displaying layered data. They draw inspiration from terrain and topographical maps, so they help create a resemblance to mountain ridges, and they're particularly effective for showing distributions over time or across different categories. So they help make complex data a bit more approachable and insightful, and color coding is quite an interactive way of displaying data in this way. So for this analysis here, let's have a look at how we're preparing for our analysis. In terms of software, we'll be using Jupyter Notebook as our development environment. Some of the key libraries that we'll be using to analyze ridge maps in this case will be essential libraries like matplotlib, which is used to chart and plot lots of different visualizations, NumPy and pandas. If you want to, say, enhance your visualizations, you could consider using other popular libraries like Seaborn or Plotly. But what we're doing to prepare to build the ridge maps using Jupyter Notebooks and Notable is, first, we need to get our data. So this could be in various formats. It could be a CSV or an Excel file. In this demo, we'll show how to import a CSV file. And once we have our data, cleaning it is crucial. So this involves handling any missing values you might have, making sure the data is normalized to ensure consistency and accuracy, and that it's structured suitably for our type of plot, in this case, our ridge plot. So it means organizing it in a way that helps us create a layered visual effect, which is characteristic of ridge maps, as you can see here on the slide. From the left, we have an Edinburgh ridge map, local ridge map here. You can start to see the Penlands in the south, which are that low mountain range we have in the south of Edinburgh forming. You can see a wider one of England in the middle, and then just visualization of what a ridge map looks like on the right-hand side. So getting a bit more practical of how we're using the ridge map library, and ridge map is a specific name of a library in Python. How we're using it in Jupyter Lab. So on the screen, you can kind of follow along with the example code on the right-hand side. The ridge map library that we're using is an excellent tool for creating ridge maps using Jupyter Notebooks. It helps simplify the process and includes all of the necessary functions already. So what we're doing here is we're creating ridge maps for Great Britain and for the Lake District, and then we're zooming in to the specific area we want when we actually execute the code. These areas have some interesting topographies, so they make it perfect and for this type of visualization. So the first step is looking at the screenshot of Jupyter Lab. The first step is to import the ridge map library with matplotlib, numpy, and pandas. Then we have to identify the points that make up the shape or the polygon, going back to our different types of geospatial data. The polygon, that's Great Britain, and this is going to help us define the boundaries for our ridge map. Then we can make sure that we have the right font and the right labeling. We want to make our text or output look clear and professional. Again, going back to that reproducibility side of Jupyter Notebooks. And we want to get the elevation values for the region so that it plots accurately and give us the height data that we need to generate the ridges. We also need to specify a color map to highlight the topographical features effectively. The right colors help us ensure that we understand and see the clarity and visual appeal, because ultimately we're quite visual creatures. And plotting the ridge map finally gives us the combination of everything. So the polygon points, the fonts, the elevation data, and the color map all are used to create a striking ridge map. So here we can have a look at the final output. On the screen, you can see the ridge map we generated using the ridge map library in Jupyter Lab. You can notice the distinct layers that represent the different elevation levels. And this layered effect is reminiscent of topographical maps that I mentioned earlier that help convey the terrain's depth and complexity. The color map and the color scheming that we can choose when we're writing the code for this output can help us highlight the different elevations in a more visual, beautiful way. Higher elevations might appear in one color, as you can see here in brown, going up north of the country. Quite significant, striking difference in the amount of higher elevation that we see. And this can be blended down into different colors for lower elevations, which makes it easier to interpret the data. And this combination of the color scheme, a clean visualization, clean fonts, and detailed layering, it gives us a visually appealing and reproducible, and most importantly, informative map. And then this type of style is useful for analysis, but also works well for presentations, for reports, and for lots of different uses. So creating this map here has shown us how there's a lot of power and flexibility in using Jupyter and the ridge map library. It's given quite a static representation, but if you have any questions about how this was written, or if you want an example of the notebook, we can make sure to share that as well. So we can see how we followed a few steps and transformed some raw elevation data into this beautiful and functional visualization in one place. So moving on to our second example, we're going to actual space. And space, more specifically low Earth orbit, is getting a whole lot busier, and is making a lot of people concerned for a number of reasons. At present, there are, it's hard to guess the exact number, but around 10,000, 9,000 operational satellites in low Earth orbit, and over double that in defunct satellites that are no longer in operation. Since 2020, there's been the requests, mostly from SpaceX, but also other contractors, to launch about 30,000 satellites into low Earth orbit. And this is in addition to 12,000 that have already received approval. So satellites have already really started to pose some challenges and disrupt astronomical observations. They've added light pollution and increased collision risks in an environment where collision could trigger a chain reaction, which could endanger current and future satellite missions, but ultimately human lives. So what this project that we're analyzing here looked at in mid-2021 was satellite counts, ownership, purpose, and the corresponding orbits of these satellites. The research here used visualization techniques that we've covered in some of the presentation already, but also spatial density charts, Gabbard diagrams, animated time series charts, and quite specific ways of analyzing data to help illustrate orbital congestion and highlight the intersecting orbits that have the potential for collision. So we have a lot of objects out in space now, and the question is, how likely are these objects to potentially collide? So in addition to satellite data, their research has explored debris in space, and using this data, the intention was to investigate several questions and present an analysis using Jupyter notebooks that could be done and used for future work. So a lot of the data here is multi-source, some open source, some becoming available after a certain time period and privately held beforehand. Other data is not yet available. A lot of the data used here comes from the Shuttle Radar Topography mission, which is a very cool mission if you want to look into it, where the payload flew aboard the Space Shuttle Endeavour during a mission and provided some of the data for this research. And it collected a lot of topographical data over around 80% of the Earth's land surface. So it was really the first ever near global data set of land elevations. So for this research, a method to have a Jupyter notebook automatically run the code was developed, and this helped avoid platform-specific schedulers or a separate backend, and helped contain all of the data and analysis in one place. So going into some of the reasoning and the of jargon used in this analysis, in the past 60 years, as you can imagine, space around the Earth has gone from virtually debris-free to a zone quite cluttered with man-made objects. And those could potentially threaten launches, active satellites, even the International Space Station. So the amount of debris has begun increasing since about the late 50s. It slowed for a decade in the mid-90s, but then the destruction of a couple of weather satellites, which we'll see in a graph in a couple of slides, helped create at least 4,000 pieces of debris. So as a result, that increased the risk of impacts to the International Space Station by nearly 50% over just a 10-day period. So there are a lot of risks and challenges in this space, quite literally. And let's have a look at some of the key points for simulating and visualizing satellite orbits around the Earth. And these use tools that we've already mentioned, like NumPy and Matplotlib, which are some of the more common packages and libraries in Python. I'll quickly go through a couple of the orbital mechanic terms showed in the image that might be of interest. Understanding terms like perigee, major axis, and inclination helps us generate orbit parameters. The perigee, as you can see in the right-hand image, is the point of the orbit that's closest to Earth of an object.
The major axis is the longest diameter of the elliptical orbit, and the inclination is the tilt of the orbit's plane with respect to the Earth's equatorial plane that runs across the equator. And using these parameters, the researchers calculated the trajectories and positions of satellites and visualized these orbits in 3D. So an interactive visualization was developed using features in Jupyter notebooks that allow to manipulate 3D plots directly within the notebook. And combining these tools within Jupyter notebooks help simulate orbital congestion and how orbital mechanics come into play when we're tracking satellites and simulating the future trajectory of satellites and the risk of a potential collision. Before going into that visualization and kind of the final output that was developed from this research, a quick note on the different data resources and methods that were used for the satellite tracking and analysis. They might be of interest. Spacetrack.org offers historic and current data sets for satellite tracking. It can be accessed via an API, and it's quite a comprehensive repository for information on satellite positions, and that in turn was crucial in this analysis for accurate tracking and simulation. There's also the Satellite Orbital Congestion Reports Assessing Threatening Encounters in Space, Socrates for short, and that's a critical tool to help assess the likelihood of satellite collisions, and it does that by using recent satellite location and orbit data. So it can calculate the probability of two satellites colliding and then help predict and avoid those potential collisions. And it's really aimed at ensuring the safety and longevity of orbital assets. And NASA has also provided a detailed history of satellite breakups with its history of on-orbit satellite fragmentations resource. And that's really helpful in understanding the origin of debris in space, perhaps because NASA's caused a lot of that from the early days, but it's become a very helpful resource, and it was used in this analysis that we're having a look at. And so to effectively use these data sets, you can imagine we need to employ various data manipulations and methods. They involve gathering, organizing, cleaning the data before you do the analysis. So if we need to handle any missing values, like mentioned earlier, normalize the data sources that we see here on screen, that needs to be done to be able to fit our analysis framework and transform the raw data that was sourced from these sources into the actionable insights that we can see over in this slide, for example, where we can see some key trends in the overall growth of space objects that has gone up. And this matters because the growing number is leading to increased congestion in Earth's orbit. And the data is underscoring the importance of international cooperation in helping to formulate policies, as well as the need for regulation to manage the launch and disposal of satellites if they're only going to be increasing with time. And here's that really rich final visual that was developed, a really vivid visualization of space debris surrounding our planet developed from this research. It's really a dynamic view of the space debris as it orbits Earth. Each dot represents a piece of debris been increased for scale so you can see it better. And it includes things from defunct satellites to fragments from collisions or explosions. You can notice the concentration of debris in certain regions, like the area around the equator, and certain low Earth orbit altitudes where many satellites operate is particularly crowded. And geostationary orbit also shows quite significant debris accumulation. So this helps us visualize and understand a particular concept, so in this case, the concept of the Kessler syndrome, which is that scenario where the density of objects in low Earth orbit being high enough that collisions between objects could cause a cascade effect, creating more debris and increasing the likelihood of further collisions. So, the raw data might help decision makers understand what's happening, but something like this might perhaps be that little bit of extra visualization that helps really understand that the trajectories, the speeds of these objects are vastly different, and it's a vastly complex environment that these active satellites must navigate nowadays because of the history behind. So as you can probably tell by now, some believe that congestion in low Earth orbit will reach a tipping point in the near future, while others believe that the issue is not hugely imminent due to the speed at which objects decay compared to other orbits. So this analysis found support for both arguments of that as significant differences in satellite decay speed is observed between lower and higher orbits within low Earth orbit. Sorry about that, just lost the slide for a second. But what this research also found is a meaningful conjunction in predicting that it's no longer possible due to the increasing number of satellites and precision limitations to reliably track what the future of this congestion will be without adding significant compute power to the analysis and without adding significant analytical models. So in future studies, machine learning techniques using non-public data that might be provided by the US Space Command will be used, which can help more accurately analyze the impact of increasing low Earth orbit density on collision probability. So at present, just to wrap up this slide, there are several satellite constellations in orbit around the Earth. The graph here models at a very high level from the data that was used what this future spatial density could look like in low Earth orbit into the future. So now we can start to think about how this geospatial data gives us insights and what we can learn from this geospatial data. The presentation has looked at demonstrating the power and necessity of combining advanced geospatial analysis. We've had a look at ridge maps, which discussed the UK map example and showed how geospatial data can visualize and solve real-world problems. And then we see how it's helpful in addressing low Earth orbit congestion, which requires a blend of advanced technologies like autonomous systems and machine learning models. It will require strict international regulations and innovative solutions for debris management. So the significant growth in satellite launches mandates some proactive collaboration, and tools like Jupyter can help embrace and expand the use of advanced geospatial analysis methods to help in decision making. So as we move into our conclusion, we can take a moment to appreciate the significance of geospatial and code and how they come together. The image here on screen represents the capability of satellite data, from capturing urban development to monitoring environmental shifts. Handling vast data sets nowadays poses significant challenges, including the data volume, manipulation, and the need for visualizations. And this is where something like Jupyter comes into play, in providing an interactive environment that's tailored for uses of code like in geospatial analysis. And so the case for code, the case for mapping new horizons and new maps with code, it's not just theoretical, it's driving real progress. So now let's move on to the next slide and we can start wrapping up how Jupyter is transforming geospatial analysis and empowering professionals in the field. So Jupyter is that integrated environment that brings data analysis together. To summarize, it's a one-stop solution for handling geospatial projects. One of the standout features of Jupyter is helping create dynamic and interactive maps with a number of different tools. And as it's a Python-based environment, it allows for extensive customization where you can adapt it to fit specific project requirements and needs, from building ridge maps to orbital congestion. And it's also really helpful to work beyond your individual codes for reproducible research. So it facilitates the sharing and analysis of workflows in a team environment. And that's really helpful for the transparency and reproducibility of code and of research. And it helps benefit the community of Jupyter at large, because everyone involved is so active, and it provides a robust set of support and rich resources. And this means that there are currently abundant tutorial extensions and integration opportunities available. And I'd recommend going back to some of those earlier slides, some of those applications of Jupyter that you can access on the web or on your device. So to wrap things up, and I'm just keeping an eye on the time here, 1 minute before 1:30. So to summarize, Jupyter is a powerful, flexible, and interactive tool that helps meet the diverse needs of geospatial professionals, as well as those working in academia and in research. It provides a set of comprehensive features, and its existing strong community support have helped make it an invaluable asset for data analysis and visualization. So hopefully I've been able to shed some insights into how Jupyter is being used, and you've found some of the examples we've demonstrated this morning interesting. So just last here on this slide, I've shared a couple of links. There's a QR code to a survey. If you have a couple of minutes now at the end to follow that QR code, it would be really helpful for us to help understand a little bit about where you're coming from. and how you're possibly using Jupyter notebooks and code in Geospatial. I'll go to the chat just now and see how that's looking, see if there's any questions. And if there's no questions at the moment, I'll just ask anyone who wants to follow up with anything to go to the Noteable website and get in touch with us. So that's notable.edina.ac.uk. You'll find the details to contact us in some of those links as well, which include a number of resources and content that can be used inside of Jupyter Notebooks. And that last GitHub link there is the link to the Orbital Congestion project, which has a bunch more information and resources on how that analysis was done. So just 1 minute over the scheduled time here. I'll thank everyone for joining us, and hopefully you found that webinar interesting. Thank you for joining this morning's Geospatial Fringe webinar, Mapping New Horizons, Rich Maps and Orbital Solutions in Noteable. There will be a recording of the webinar that will be circulated after. So if you would like to share it with anyone or you missed any of the webinar, do have a look at that. And I'll thank everyone again for joining us this morning, and I'm wishing you a very good rest of the day and good rest of the Geospatial Fringe.